When measuring the mass in a lab, you would use a balance. These balances come in a number of different forms, each having a different level of precision. These are 3 different balances used in labs to measure the mass of a substance. In front is a triple beam or decigram balance, which measures the mass out to 0.01 grams. In the back right is a centigram balance that measures mass out to 0.001 grams. And on the left is a digital analytical balance, which gives a digital readout all the way to 0.0001 grams. That one would be considered the most precise. Depending on what you're using in lab and what you're going to be measuring out, the type of balance that you use could be important. If you're weighing out a very large amount of material, the accuracy down to the fraction of a gram would be less important than if you were weighing out a very small amount. As with measuring the mass, where there are different types of balances giving different levels of precision, in a lab, when you're measuring the volume, there are a number of different types of glassware, each with their own level of precision. Displayed are 3 volume measuring devices of 50 milliliters. A 50 milliliter beaker, a 50 milliliter graduated cylinder, and a 50 milliliter burette. Each of these are used to measure volume with varying degrees of precision. While the burette is the most accurate, having a precision level of 0.01 milliliters, the graduated cylinder has a precision of only 0.1 milliliters, and the 50 milliliter beaker has a very low level of precision, only down to 1 milliliter. So in this experiment, you'll be looking at measuring the density of a liquid using these different measuring devices. Measuring out the volume using a burette, a graduated cylinder, and a beaker, and measuring that mass on all 3 types of balances. Determining what the density is of that unknown liquid and out to the level of precision is critical when utilizing these different measuring devices. The first pairing to determine the density will be using the decigram balance and a 50 milliliter beaker to measure the volume. When measuring the mass of something on a balance, the material to be measured should always be placed in a container, either a separate beaker or on a piece of weighing paper. In the case of measuring an unknown liquid, it should always be placed in a container and never directly on the balance pan. When determining the mass of that material, though, the mass of the empty container then needs to be taken into account. So first, we'll need to determine the mass of this empty container using the beam balance. By placing it on the pan, we see that the beam pins up, meaning that the beaker itself weighs more than 0 grams. Starting with the heaviest mass first, we can see that the beam pins down, indicating that this container weighs less than 100 grams. We can now start to move the next weight, which it pins down, at 10 grams, indicating this container weighs less than 10 grams. The last beam is always a slider which moves along the front beam. When the beam reaches the zero line, that would be an indication that it is balanced and the total mass on one side of the beam is the same as the total mass on the other side, meaning the mass of the object being weighed. As you can see, the beam is now perfectly balanced with a final mass reading of the heaviest weight is at 0, the hundreds place is at 0, the tens place is at 0, and the final mass reading of the empty beaker is displayed. Next, I can measure out the volume of my unknown liquid using my volume measuring device. In this case, I'm using the more inaccurate 50 milliliter glass beaker. I can pour in the unknown liquid, and you can use the readings to determine what is the volume of this unknown liquid. With the volume of liquid now measured, we can add this to our container. And weigh the entire setup again. The difference between before and after adding the liquid is the mass of the unknown liquid. And with the measured volume of that liquid, you can determine its density. Again, starting with the largest mass first, it still weighs less than 100 grams. Only this time, it weighs more than 10 grams, more than 20 grams, more than 30 grams, but less than 40 grams. So it is between 30 and 40 grams. And now, by using the scale on the front and the sliding weight, we can determine what is the total combined mass. It's now zeroed, and you can see what the mass is. Now displayed is the final mass reading of the combined mass of your empty container and the liquid measured out from the 50 milliliter beaker. Using these numbers, you can determine the volume of liquid, the mass of liquid, and its density. Be sure to record the density based on the appropriate level significant figures based on the measuring devices, the beaker and the balance. For the second setup, we will be using a centigram balance and a 50 milliliter graduated cylinder to determine the density of the unknown liquid. As with the first setup, the mass of the empty container will need to be determined first. Placing it on the pan, we can see that it pins up meaning it weighs more than 0 grams. By sliding the heaviest mass first, we see that it weighs less than 100 grams. With the centigram balance, there are 4 separate masses, or 4 separate weights. Moving the first one, it's seen that it weighs less than 100 grams, and now moving the second heaviest weight, it weighs more than 10 grams, more than 20 grams, more than 30 grams, more than 40 grams, more than 50 grams, more than 60 grams, but less than 70 grams. Where the triple beam or decigram balance used a slider at this point, the centigram balance has an additional mass where you can go by the ones place to see. So in addition to the 60 grams that it weighs here, it now weighs more than an additional 1 gram, 2 grams, 3 grams, 4 grams, 5 grams, 6 grams, 7 grams, but 8 grams is too much. So with 60 plus 8, 68 grams, this beaker weighs less than 68 grams. However, it weighs more than 67 grams. It's in between those two mass readings. Using the sliding scale in the front, or the sliding weight in the front, we can now slide this along to determine what is the exact mass of this empty beaker. It's level and zeroed, so the total mass is the 60 grams plus the 70 grams plus what is displayed on the sliding scale. With the mass of the empty beaker measured and recorded, we can now measure out the volume of liquid that will be weighed. And we'll be doing this using the 50 milliliter graduated cylinder. This has scale divisions to read to 0.1 milliliters. You can now take the recording of what is the volume contained in this graduated cylinder. With the volume recorded from the graduated cylinder, we can now add this to our container and obtain the total mass of the container plus the liquid that's inside. Again, starting with the heaviest mass first, it now weighs more than 100 grams, but less than 200 grams. So this can now stay at the 100 gram mark. In addition to the 100 grams, we now move the next one. Out to the tens place, it weighs less than 110 grams, but more than 100. Choosing the next weight, it weighs more than 101 grams, more than 102 grams, but less than 103 grams. So this means the total mass of the beaker plus the liquid is between 102 and 103 grams. To measure the final digits of the mass, we can then use the slider to determine what is the total mass. So now we have 102 grams plus whatever is shown in that sliding scale. The overall weight is zeroed, and we now know the total mass of the combined beaker and liquid. Using the total mass of the combined beaker and liquid plus the mass of the beaker itself, you can determine the mass of the liquid. And with the volume of liquid from the graduated cylinder, you can calculate the density to the appropriate level of significance. The third combination will be using a digital analytical balance and a burette. The digital analytical balance is the most accurate form to measure mass in general chemistry labs, going all the way to 0.0001 grams in its precision. The burette is the most accurate way of measuring appreciable volumes in general chemistry labs as well, going out to 0.01 milliliters. Burettes are very long, narrow tubes with graduations where you can see what the measurement is. As these are very long and narrow, they should always be supported on a ring stand with a clamp. This ensures that they're properly level, as well as that they don't roll off the countertop. At the bottom of a burette, there is a valve that controls how much liquid is released from the burette. This should typically be in the off position. The off position is perpendicular to the burette itself. When you're wanting to dispense the liquid, you can open the valve and have it be parallel with the barrel of the burette, which would release the liquid. Before filling, you should always make sure that the burette valve is closed. With such a narrow opening in the burette, a funnel should typically always be used when filling the burette. This can be placed in the burette, making sure that the valve is closed, and the liquid to be measured can be added. Burettes are read from the top down, meaning that a full burette has a volume reading of 0.00 milliliters. When filling a burette, it is usually easier to overfill the burette and then accurately release some of the liquid from the valve, allowing you to measure precisely where the initial reading is. Burettes are very accurately calibrated to know precisely how much liquid is dispensed. And this is under the assumption that the entire burette is full, including the tip. So before you use the burette, you should always make sure to release some amount of liquid from the bottom, just to make sure that the burette is completely full and the measurements are accurate. Before dispensing the liquid in the container, we first need to know the mass of the container. On the digital analytical balance, because it is so sensitive, many times small adjustments might need to be made. Initially, you want to make sure that when the balance is empty, it is reading exactly 0.0000. If it's not, you can then press the tare button on a balance to clear it and make it read 0. Once you have the balance taired, you can then open the window and add your container. Waiting for the balance to stabilize, you can then see the final measurement on the screen now. Burettes do not need to necessarily start exactly filled up at the 0 mark. They can start anywhere along the entire barrel. This is because burettes measure how much liquid is dispensed or leaves the burette and enters into a different container. To determine how much liquid is dispensed, the two burette readings are taken, both the initial burette reading and the final burette reading, both of them out to 0.01 milliliters. You can see the initial reading here. When the valve is then opened, the liquid starts to decrease as it is being dispensed into a container below. While this is dispensing, the mass of the liquid in the container is also increasing along with its volume. After the container is after the liquid is dispensed in the container, we can then obtain its total mass and determine the density. Now that the valve is closed, we can see the final burette reading here. You can use the initial and final burette reading to determine how much liquid was dispensed into the container below. With the liquid dispensed from the burette into the empty container, we can now use the digital analytical balance to record the total combined mass. Again, making sure that it's starting as exactly 0. We can add the container to the balance and record the final total mass here. Using this mass, as well as the starting mass of the empty container, we can determine the mass of the liquid itself. And based on the volume dispensed from the burette, we can calculate the density out to the most appropriate level of significance. Typically, on such a sensitive balance, even things like water or this unknown solution can slowly decrease in mass. This balance is sensitive enough to detect even the evaporation of water. Typically, if using a balance such as this for much more accurate measurements, you would want to have a closed container or cover the container to prevent that mass loss.